Okay, today we're talking about wave motion. The first two types of waves we're going to look at are transverse waves and longitudinal waves. Okay, so a transverse wave is a wave whose wave motion is actually perpendicular to the way that the wave is moving. Okay, so if you take a note up here in this, let's do this in green. As the wave moves to the right, the wave is actually moving up and down. Okay, if we look down here at the bottom left, here our wave is moving to the right again, and yet the amplitudes are up and down. So notice that the angle between those is 90 degrees. These are perpendicular to each other. Now let's contrast that with a longitudinal wave that's actually moving in the same direction as the wave crest, if you will. Okay, so here our wave is again moving to the right, but the compression here is also in that same dimension. Okay, so the compression is moving to the right. The expansions are left and right as well. So here, compression and expansions left and right. The wave is moving left and right, so they're all in the same dimension. Okay, so those are the two basic types of waves. Up in the top right, they're distinguishing between pulse waves versus in the bottom left we have what are called periodic waves. In the top right, pulse waves are just single crests or single troughs that are sent along the wave, whereas in the bottom left we have periodic waves, and those are just repeated over and over and over again. Okay, let's look at our next slide here. Here we're going to look at interference. Okay, so if we have two pulse waves that are traveling toward each other, as shown right here, as shown, let's do this in red, right here. Okay, what's going to happen when they collide? Well, here they are getting a little bit closer to each other. They're still moving toward each other. When they collide, they're actually going to add their amplitudes. Okay, so here, notice we have two small crests added together to make one big crest. Now, after they pass through each other, they don't continue to add together. Once they're past each other, they just keep going as if nothing happened. And here they go like that. So it's only when they happen to line up in the middle where we actually get interference. Now, this is called constructive interference because the two waves add together. The two crests add together. They're on the same side. Now let's look at destructive interference on the other side over here. We have a crest. This is going to meet a trough. So when they meet together, they actually cancel each other out completely, and we get no amplitude while they meet. However, they don't delete each other forever. They keep moving. So they keep moving here, and after they're past each other, they keep going like nothing happened. And that's destructive interference right here in the middle. Okay? Looking at the bottom, we have what happens if periodic waves interfere with each other. Well, if they're lined up crests with crests and troughs with troughs, then you're going to get constructive interference. The crests are going to get bigger. The troughs are going to get bigger. But what happens on the right side if we have destructive interference? Here I have a crest that's lined up with a trough. So when you add those two together, they actually cancel out. We get nothing. Next wave, we have a trough lined up with a crest. Those cancel each other out. We get nothing. So these two waves on the left are what's called in phase because they're crest with crest, trough with trough. They're all lined up. But on the right, we have out of phase because the crests are lined up with troughs. They're exactly opposite. Okay, let's move on to our next slide. Now we're going to talk about standing waves. Okay, standing waves happen a lot of times with sound or with light. A lot of different scenarios where they pop up. But there's three different ways that they can stand up. Okay, the first would be if both ends of the wave are forced to be tied down. Okay, as though imagine it's just like a string that's being tied down on each side. Okay. These points that cannot move are called nodes. Label those with N's. And this point in the middle that's able to bounce up and down is called an antinode. Okay? That's the first standing wave. When you move down to the second one, you could have, in the same distance, you could have the same amount of, in the same distance, you could have the same string, but setting up the second standing wave. So here we actually have 3 nodes. Notice there's one here, there's one in the very center, and there's one on the far right. And here we have 2 antinodes. So here we have 3 nodes and 2 antinodes. So what you want to think is that these waves, the crests aren't always crests. They're kind of going up and down. And then it'll be here, and then it'll move down, and it'll move like that. So it's constantly moving from the top down to the bottom, from the top down to the bottom, and the opposite over here. So these would be moving from the bottom up to the top, and then the top down to the bottom, just repeating themselves like that. Okay? And we can keep doing this. The third standing wave, the fourth standing wave, the fifth. Here we add another node and another antinode. So now we have 4 nodes and 3 places where we're going to have antinodes. Alright, and this is like a string that's been tied down on either end. But what if you have a setup like where it's a pipe that's open on both ends? There's a lot of musical instruments that look just like this. So let's say both ends are open. Well, that's going to force both ends to be antinodes. And the very center is a node. So you're going to have a permanent spot that doesn't move, like a trough right here in the very center. That's a node. And in the antinodes, there's going to be crests that bounce from the top to the bottom. All right. So here we have, when we move on to the next one, we just add another node, another antinode. Let's draw those antinodes in there real quick. Okay. And then we go to the next one. Now we have 4 antinodes and 3 nodes. I've drawn my 3 nodes. Here are my 4 antinodes. Okay? So each time we move one to another, and just different musical instruments get set up in different types of standing waves. Here's our last scenario where we have a half open pipe. So here we would have a node on one end and an antinode on the other. Okay? And we move to the next one, we add a node and an antinode. So now we have 2 nodes and 2 antinodes, 3 nodes and 3 antinodes. So notice that if you can remember how each one is set up originally in this very first level up here. That was a terrible circle. Let's try again. In the very first layer up here, if you can remember how these are set up, then you just remember that each subsequent standing wave is going to add 1 more node and 1 more antinode. 1 more little crest peak. Okay? Let me finish drawing these in here. We have 3 antinodes down here. Okay. Now what if you actually want to do some calculations with these? It turns out that we get a formula that looks something like this. It says frequency is equal to N times V over 2L. And this is the formula that applies to these two. And then we get a slightly different formula over here for the half open. And it says that the frequency is equal to NV over 4L. Okay, let's see why there's that difference. Over here on the left, you're counting how many wavelengths there are. Okay, so if we look at this very first one, there's actually half of a wavelength. It just goes from here through a crest and then stops. In order to do a full wavelength, it also have to go all the way through a trough and back to the beginning. Let me just draw that over here real quick. This would be 1 full wavelength, right? And if we draw the other side as dots, we get this. Okay, so this portion, where did my okay, this portion right here is just half of a wavelength. Okay, so that first standing wave is half of a wavelength. So if we were to solve this right here, we would plug in 1 for n because it's half of a wavelength. Well, what does V stand for? What does L stand for? V is the velocity of the wave. L is the length of the string. Okay, and that'll tell you the frequency of that wave. What if we had to do the second one? Well, this is actually a whole wavelength. It goes through the whole cycle. So then this would be 2 over 2 wavelengths. What if we had to do the third one? Well, this right here is a full wavelength, and then you have another half wavelength. So you actually have 1.5 wavelengths. So you would actually do 1.5. So 3 over 2 V over L. Okay? So you're counting how many half wavelengths there are. But if you look over here, actually before we move on to the 4 formula, let's look at the open pipe, the second column. We actually have how many wavelengths? Well, you start at a crest and you move down to a trough. So that's actually half a wavelength again. So this first one, we would use n equal 1. For the second one, you start at a crest, you go through a trough, and you go all the way back to a crest. So that must be a full wavelength. So we're using 2 over 2. The bottom one, again, we start at a crest, go to a crest, but then, so that's one full one right there. We've already done one full one. Now we go from the crest to a trough, that's half of a wavelength. So again, we're at 3 over 2. So we're going to use n equal 3. Okay, so both of these scenarios use this same formula right here, right there. Okay. However, when we go to this half open pipe on the right, we're going to get a slightly different formula. And that's because what portion of a wave have we drawn? Let's draw one full wavelength. We've actually only drawn from the beginning of the wave up to a peak right here, up to a crest. So it turns out that is a quarter of a wavelength because you have 1, 2, 3, 4 pieces that look just like that. Okay, so that is a quarter of a wavelength. So that's why n starts like it does right there. Let me erase this so that I can do some math here. For our very first one, we would plug in 1 because it's 1/4 of a wavelength. For our second one, we would go, well, it goes through half of a wavelength, and then it has another little quarter wavelength. So that's 3/4 of a wave. So we would actually just plug in 3V over 4L, 3/4 of a wavelength. And then for the last one, we go through one full wavelength, and then another quarter. So that's 5/4 of a wavelength. So these are standing waves. It tells us the frequency of the wave. If this is sound, as though these were musical instruments, imagine this string is a guitar string, or this pipe is some sort of trumpet or trombone. Okay, you can tell what the frequency of the sound coming out of it is based on this formula right here or this formula right here. Okay, NV over 2L or NV over 4L, just depending.